and then we'll take it from there. Hello everyone. My name is Sergey. I spent around 6 years in Percona. I've been their head of product, and then we decided, okay, we need to spin up our own company called Solanica and take Percona Everest from Percona and make it Open Everest. So today my talk is about the simplicity. And at first we're gonna start with some universal human drive for simplicity. We're gonna look what kind of simplifications humans are actually doing and interested in. Then we're gonna look into the simplification in IT. And then the most interesting part, as usual, is databases and how people tend to simplify databases. So for universal drive for simplicity, this is how we travel on the ground. So it all started a long time ago with horses. Then it were carriages. And then Henry Ford came in and created the first car. And when Henry Ford said, okay, why did he create the car? He said, okay, if I were asking people what do they want, they were telling me, hey, we want faster horses. We don't want cars. They didn't know what cars are and if they can exist, right? And then we had a car with 3 pedals. I don't know if anyone had this car. I had. So it's regular 3 pedals. You have a clutch, a brake, and the gas, and you have a manual shift. It was annoying because you need to change the shift, especially in a traffic jam. It was crazy. You were tired, and so on, right? Then throughout some years, now I don't think we have a lot of cars with manual shift. More of them are with automatic shift. And in the States, for example, people are saying that, hey, if you have a car with a manual gear, then it's a good anti-theft device because not a lot of people know how to drive those. Yeah, it's really like that. And the next simplification, we also now have self-driving cars. You don't need to do anything, you just sit in it and it drives you whenever you want. So we don't really want to shift gears anymore. What we want to do is want to travel from A to B. And the way it's simplified from carriages to self-driving cars is just natural for humans, how we think about things. We're lazy, let's be honest, but also we just don't want to do a lot of manual things. Another good example of simplification is in cameras and in photography. So who knows what this thing is in the left corner at the top? You can speak. Huh? Correct. It's a dark room or camera obscura, like, right, how it's called. It was there, I think, since the 5th century. And the way it works is that you have a dark room and a small hole in the wall, and the image from the outside was projected to the wall upside down, right? And that's actually how all the cameras in the past were working, and all modern cameras today actually work, is that you have a hole, and through it, the light is projected to some matrix, or like in ancient cameras, it was some silver nitrate and so on. So some chemical reaction was happening, but overall, that's how the cameras worked and how we were drawing and so on. And then after some years, we jumped to another level of simplification for cameras. We had cameras with film. I don't know, again, if somebody remembers this Kodak and so on. We're not that old yet, right? But then we had digital cameras where you were taking a photo and you immediately see it on the screen. And Kodak was no more. And nobody is using films today, at least not like even in professional setting. Most people are just using huge cameras who are professionals. And obviously now we have cameras in our phones, we're doing selfies, nobody is carrying a huge camera unless you're a professional, if you're doing something professionally for that. And yeah, everyone's taking selfies or taking photos with their cameras. Who knows what it is? Exactly, yeah, it's SpaceX. So SpaceX had this evolution of engines. from left to right. It's Raptor 1, Raptor 2 is just the code name that they use for these engines. And if you look at Raptor 1 or Raptor 2 and compare it to Raptor 3, you immediately see that there's a lot of different tubes and plumbs and so on, right? And as plumbers were saying, or mechanics were saying, it's a complete plumbing nightmare to manage these engines and so on, because each tube required its own protection from the high temperatures. You need to make sure that each tube is kind of connected correctly and so on and so forth. And over the years, SpaceX was improving their engines and made Raptor 3. And Raptor 3 is kind of interesting because all these tubes are still there, but they were actually metal printed. So they're inside, and they printed the whole engine with a huge 3D metal printer, actually. And that's quite interesting because now they don't have this problem anymore with connecting all these tubes and making sure that they fit and so on. They don't need to protect them from the heating and from the friction and so on. And what is also interesting is that Raptor 3 not only simpler, but it actually gives a better thrust and a better ratio. So it's more powerful at the same time. It's more light and it's more beautiful, right? So now let's talk about IT a bit. And again, old computers started, I'm not that old, but I read about these huge computers that were taking the whole room. And to do something on this computer, you had tumblers. You set these tumblers, you press a button, and you wait for a few days, and then you see a result on some piece of paper or on these tumblers, whatever, or on some lamps. Who knows what's that in the middle, at the top, the yellow thing? Huh? Correct. It's punch card, right? Punch. Yeah, I have them as well. Yeah. That's pretty wonderful thing. So the way they worked, for those of you who don't know, is that you punch the holes in these punch cards. You see there are zeros and ones and so on. And each card represented a single line of code or some sequence of numbers that you are inputting into a magical computer that it then is doing something, right? And then throughout the evolution, who knows what's this language on the right? Correct, that's assembly. Oh, you see, we're getting there. So yeah, it's assembly, and it's hello world, and it's actually a few pages more of the text to just print out hello world on the terminal. So it's quite lengthy. And then basically it's C or it's C++, then Python is just a single line of code now to print hello world. And now we are in the era of wipe coding, where you just ask AI to build you a nice fancy application, and that's it. I think it's the screenshot from VS Code. And another era of simplification is cloud computing, is when big cloud providers are coming in and saying, oh, you know what, you don't need to manage your servers anymore. You don't need to set up the networking. You don't need to learn how it works. We're just going to give you a computer or an SSH endpoint that you need to connect to, and you have everything working with ease, right? But the reality is that there is no cloud. It's still someone else's computer or virtual machine. They just provide you the interface. And there is some lies there, and usually when we talk about clouds, the first lie is that it's fully managed service. And it really is. When you have an RDS, when you have some other Redshift service or whatever, it's fully managed. But at the same time, the lie here is that you still need engineers to work with these technologies, as Jericho was talking today. You still need someone smart to do that. And that's why we have actually cloud engineers who are highly paid engineers now in the States with an average salary around 160K. So it's quite a lot. And we have a lot of them. Instead of system administrators, now we have cloud engineers. Okay. Another lie is that it's cost effective. It may be cost effective for big clouds, but it's not so cost effective for companies who are using cloud technologies. Because there are gazillions of other businesses who just help you to bring your cloud bill down, which says, oh, it's not that cost effective. It's still hitting your wallet. And you're in control. The reality here is that, yeah, they tell you that your data sits in region A, B, or C, but you can't verify it. You can't know if some Amazon engineer is going to log into your EC2 instance or read your data and so on. You don't have control over it at all, right? And it's kind of trust. You trust Amazon that they are not going to screw you up. Yeah, and this is where getting closer. So this is another evolution from for virtualization or for containers and isolation. So who knows what root is? CH root. What is it?
Well, that's a technique for you to isolate your OS inside of it. You can change your root space so it feels like you are inside of another environment. You can still do it nowadays.
Correct. It's still even used today. It's just to tell the process that, hey, you actually run in this isolated folder, in this isolated environment, and that's it. With root, you can't like limit the number of CPU that the process is using. You can't limit the RAM or anything. What you can do is just run it in isolated folder. Say you don't touch any other files. That's it. And it was the basic isolation available even in Sun operating system in Solaris. Then in 2000, FreeBSD jails came in. I don't know if anybody ever used FreeBSD here. Yeah, I used it a lot as well, and I used FreeBSD jails. It's quite a nice technology, and it also already there provided you a way to separate processes on CPU level, on RAM, and so on. Then C groups came in, then LXC. LXC was just based on C groups, and here on the left you see an example of how to create a C group and limit some RAM and CPU for some specific process or program that you run. And then in 2013, something magical happened. Docker appeared. And what Docker said, okay, C groups look so complex, we can actually simplify that. And instead of running all these commands, we're not going only to allow you to run this simple, shorter command, but we're also going to allow you to build your container images and store them somewhere with a nice Docker build command. And everyone was immediately using it because it was super simple, and everyone understood that, oh, with Docker, we can actually recreate our environments easily locally or some remote server. But the essence of Docker is still that it uses C groups. It's still relying on this same technology that was invented years before. So that's how simplification works. You do something simple and people immediately start using it. And then in 2014 and till up now, we have what is called Kubernetes. Kubernetes is just an orchestration for Docker containers or for any other containers. Now, they don't use Docker under the hood. But what it does is just moves one container from one node to another, creates load balancers, simplifies container management at scale for anyone. Yeah. Well, Kubernetes is still complex, but it serves the purpose. It still solves the problem of moving one container to another node. Yes and no. Yes. Yeah. So now let's talk about databases finally. So databases were always the child that you don't really look after. All engineers, they have all these fancy tools for running their applications, their DevOps practices to run applications and so on. But databases are often neglected. They are not given the love they deserve. And what is also interesting is that databases are always treated as precious pets. So again, all engineers, they say, okay, this is my application. It has many containers. It has many VMs. I'm going to shut it down because it's stateless. Nothing is going to happen with my application. But if I touch database, everything is crashing. right? So it's still a precious pet. I don't want to touch that. And when we talk about databases, there are today usually 3 doors that you can go into. Door number 1 is, I call it legacy, but it still exists and widely popular across different environments, is when your developer needs the database, the ticket is created, then some scripts are running, and developer gets access to the database. Then, obviously, managed services, they are saying, oh, we're going to solve it for you. You don't need any scripts. We're here for you. We're going to give you just an RDS. You can connect to it and run. And then the third door is cloud native. I'll talk more about it next. And there are no good doors or bad doors, but I like to think about these doors as marriage. You can enter one of these doors and find out that, well, it doesn't work for you. It's complete disaster, right? Or you can find the love of your life and live happily ever after forever. So it depends what your preferences are. So if we talk about RDS again, is that RDS is like this rental car. And there is the paradox that with RDS, you have all the all the simplicity you want, but you still have vendor lock, and you need to pay for it eventually if you want to move out, if you want to move your MySQL from RDS to Google, for example. It's still a lot of work. It's still egress costs, it's still the cost of engineering, and so on. Now, clouds also say, you know what, scaling is super easy. And with clouds, it is super easy, but at the same time, the cost of it increases significantly, especially if you want to scale throughout multiple regions. It's 3x. If you want to scale through multiple regions, no, AZs, it's 3x, and multiple regions, I think it's 5x or more. And if you can run something like Aurora serverless, which is like, can skyrocket your costs a lot. And there are also hidden costs with RDS or Aurora, like IOPS. Sometimes people forget about IOPS, and then they see their bill and they know, oh, looks like my database is consuming more resources than I was thinking. And some outages in the cloud, they also happen, or in the regions or in the availability zones. And what Amazon usually tells you, oh, you need to run across multiple regions, but we go to point 2 where it costs a lot. And the dilemma is the following. So I have RDS or some managed service, and I'm happy with it. It works nicely, but I'm this in total captivity. Or I have this do-it-yourself kind of approach or open source technologies, but it comes with significant trade-offs. And we're usually forced to choose between these two. Either I pay a lot of money and I'm locked in, or I don't pay anything to some vendor, but I don't have agility, I don't have flexibility, I don't have anything. And the wish is simple, is that, okay, I don't want any trade-offs at all. I want to be sure that if I use open source or if I use something on my own, then I have great experience. And it's still simple, it's still not over complex, I don't need to fight the complexity. I want to treat my databases as cattle. I don't want to treat them as precious pets. I want to be sure that if my replica or my primary goes down, then everything is still working fine. And we can apply all these fancy tools to databases like GitOps and so on and so forth, and other best practices. So again, we are not going back to this picture where the child is drowning and neglected. And the usual answer today to this is cloud native. And there is a huge cloud native ecosystem with all the projects in it, and they're widely used in production. And for databases, whenever you think about, okay, how do I run databases in cloud native system, it's usually the answer is, okay, you need Kubernetes and you need operators. To simplify what operators are, is just a code with some wisdom encoded in it. So you say to Kubernetes API that, hey, I need a Postgres cluster, I need 60 gig of storage, I need 3 replicas. You define what you want, you define your desire. And then the Kubernetes operator that runs in Kubernetes just spins it up for you and gives you the endpoint to connect to. That's the magic behind any Kubernetes operator, and that's the usual recommendation how it works. The problem with operators, though, is that they are simplifying things, but they're all different. So you have cloud native PG, you have Altinity, a ClickHouse operator, you have Percona operators, and they're all different, not only in the way you configure them, but also in the way how they integrate with other tools, how they use monitoring and visibility tools, how they use backups and so on, and you need to learn that. And sometimes the learning curve is kind of steep. So what we're doing in Solanica, we took Percona Everest, we named it into Open Everest. We're now open source. We open sourced it. Well, it was open source, but we're pushing harder on it. And it's production ready product. It's deploying already thousands of databases overall, looking at our telemetry. And it's going into Sandbox, but the CNCF Sandbox, but I'll talk more about it on the next slide. The way it works is that the user talks to either web UI or API or through a command line to Open Everest, and then Open Everest creates the database, and then user connects to this database. So it's kind of similar to the cloud, right? You have a web UI, you click a button, you get the database, you connect to it, and that's it. It's what we do with Open Everest. If you look at the, oh no, that's UI. That's how UI looks like. It's just an example. And if you look a bit deeper into how Open Everest works and what's so different with it, is that we have what we call a master custom resource, which is a CRD in Kubernetes. And it actually relies under the hood on different other battle-tested operators like Cloud Native PG, Percona operators, Altinity, and so on and so forth that we also plan to add more through pluggability. And also the beauty of it is that all these operators, they are really battle-tested. So there are some products out there that try to implement their own management layer for databases, but the reality is that Percona knows what they are doing with MySQL, for example, or with Mongo. They know very well how Mongo operates and how MySQL operates, and you don't need to imagine or invent how to take backups, how to scale it. They all have it encoded in the operator already. And what it is needed is just to make sure that these primitives that Percona created are exposed through Open Everest. And this picture is kind of famous. It's all the projects in cloud native ecosystem, and we can integrate with almost any of those. And they allow you to scale better, they allow you to have better security, better observability, and so on and so forth. And that's the beauty of cloud native ecosystem overall. As for the roadmap for the Open Everest, we're working on modular core. It's going to be shipped somewhere pretty soon, March or April. And what does it mean is that anybody can easily add their own database technologies or their plugins into Open Everest, and that's where we expect the biggest boost in terms of contributions, in terms of open source collaboration. We applied to CNCF Sandbox, and yesterday it was kind of approved. Now we're in this voting stage, and soon we will be in onboarding stage, hopefully. What it means for the community is that Open Everest pledges that it's going to stay open source forever. We are not going to be able to change the license even. It's now Apache license, and if it's CNCF governed, it must stay the same because we donate everything, the rights to CNCF. And yeah, integration, I talked about it. So yeah, thank you. I encourage you to join our community, to follow us on GitHub, connect with us in Slack channel. And if you're looking for some commercial services for Open Everest, we at Solanica and Percona are also providing those. Thank you.